Hello everyone, I'm Hanlin. In this video, I'm going to introduce combinatorics. It's regarded as one of the most challenging parts of math competitions. We will start with the classic Lattice pass problem, then move to a relatively advanced concept, the Catalan number. So, let's get started. So what is a Lattice pass problem? Imagine you have a 5x5 grid. And there's a person who have to move from the bottom left corner with a coordinate 0, 0 to top right corner with a coordinate 5, 5. However, there are some restrictions. So for each step, he's only allowed to move 1 unit to the right or 1 unit upwards. The question is, in how many ways can he move from the bottom left corner to top right corner? Here are 3 passes that satisfy the given condition. So what do these 3 passes have in common? And as we can observe, they move 10 steps in total. Among these 10 steps, there are 5 steps to the right and 5 steps upwards. We use U to represent the upward steps and R to represent the steps to the right. For example, our 3 passes shown could be represented like that. It makes sense because during the whole pass, the x coordinate changed from 0 to 5, which means the person moved 5 steps to the right. So there's y coordinate and 5 upward steps. Now our question could be converted as in how many ways can we arrange 5 u's and 5 r's? Because each arrangement of these letters correspond to a unique possible pass. We just need to know how many arrangements are there for 5 u's and 5 r's. We draw 10 slots to put these 10 letters. We choose 5 slots to put these 5 r's. There are 10 choose 5 ways for this. And after we choose which 5 slots to put 5 r's, we can only put u's for the remaining 5 slots, which means there's only one way for the remaining 5 slots. So, the final answer for this problem is just 10 choose 5. Now let's generalize this type of problems. What if our destination is Mn? Similarly, the person moved m plus n steps in total, and m steps to the right, n steps upward. By using the same approach with slot and lattice, we got our answer should be m plus n choose n. Wait, is that the only approach of this problem? Of course not. We can solve this problem by adopting another seemingly entirely different approach. Let's go back to the 5x5 grid, and the same problem as before, but now we are not focusing on the arrangement of steps. We label each point with a number of ways to reach it. It seemed hard to notice that a number for 5, 5. So we can start with easier ones. Notice those 2 lines. The number of points on these 2 lines are easily to determine because you have to always walk to the right or walk upwards to reach the destination. So there is only one way for these points on the line. Now we should think about other points. For every point excluding the origin 0, 0 and points lying on those 2 boundary lines. Every lattice pass leading to this point must pass through either the point directly to its left or the point directly underneath it. Why is this? Consider the final move before reaching the destination. By the problem setting, the last move can only be 1 unit right or 1 unit up. And this validates our previous deduction. Now we suppose we aim to reach the coordinate Mn. We define PAB as the total number of the passes from starting point to any lattice point AB within the grid. All passes terminating at Mn fall into 2 disjoint categories. The first one is passes that first reach m-1n, followed by a single step to the right. And the second one is passes that first reach m-1, then take 1 step upward. As we said before, there exists exactly one valid final move from m-1n or mn-1 to mn, either moving right or up accordingly. Hence, the quantity of the first set of passes equals pm-1n, while the second set amounts to pmn-1. Summing these 2 values gives us the total number of passes to mn. Establishing the recurrence relation, Pmn equals Pm-1n plus Pmn-1. This formula implies that once we know the pass count of the lattice point to the left and the lattice point underneath, we can compute the pass count of any point by just adding them up. And look, this is how we get to our final answer by just the recurrence relationship I give you. You just have to do the same thing on repeat. And see, our final answer is 252. Now we have already solved these problems in two ways, but there's some more interesting conclusions about this problem to discover. In the first method, we got our answer in the form of binomial numbers. In case you don't know, here's a formula to convert any binomial number into an integer. And also, if you don't know what does a factorial means, here is a definition of a factorial. And in the second approach, we got our answer by the recurrence relationship Pmn equals Pm minus 1n plus Pmn minus 1. From the conclusion of first method, we know Pmn equals n plus n choose n, and Pm minus 1n equals n plus n minus 1 choose n. Pmn minus 1 equals n plus n minus 1 choose n minus 1. For simplicity, we let n plus n to be a and n to be b. And now we get this identity. It's a very important identity in combinatorics, and we'll also talk about it again later. Now let's go back to the pass count when we finish this problem with the second method. If you're familiar with Pascal's triangle, you will find out that actually the number along these lines exactly match those in Pascal's triangle row by row. And we're just missing the one on the top. And there's an interesting property about Pascal's triangle. We notice that each number in Pascal's triangle equals the sum of two numbers diagonally above left and above right. And the group of number we just highlighted show exactly how this works. And actually, that could be explained by the recurrence relationship we got from the grid or the identity we just proved. Now let's change the condition for our problem a bit. The movement rules stay the same. The person can only take one step right or one step up each time. But now, any region where the x-coordinate is bigger than the y-coordinate is dangerous. And in other words, everywhere below the line y equals x is dangerous. And we cannot step there. We want to go from 0, 0 to nn. How many different passes are there? This is the upper half plane problem. If we ignore the dangerous zone, this would just be the lattice pass problem we talked about a moment ago. From our earlier reasoning, we need exactly 2 n steps in total. Choose n steps to go up, and the other n steps to go right. So the total number of passes is a binomial coefficient 2n choose n. But here's a problem. Among all these passes, many cross the safety line y equals x and go down into the dangerous area below. How many such dangerous passes are there? The first solution is actually really clever, and it's my favorite solution. We can solve it by using one-to-one matching. You can also call it bijection if you want. So for every dangerous pass, it first enters the dangerous region below y equals x by taking the right step from some point kk on the boundary line y equals x. And that takes us to k plus 1k. Notice that all these points lie on the line y equals x minus 1. So the very first point where we step into danger always sits on y equals x minus 1. The next step is the most important. Now we reflect every segment of the pass that comes after this first dangerous point across a line y equals x minus 1. After this reflection, the original endpoint nn gets mapped to its mirrored counterpart n plus 1 and minus 1. And we can convert every dangerous pass to nn into a normal pass to n plus 1 and minus 1. Here comes another really cool part. We just saw how to turn any dangerous pass to nn into a pass ending at n plus 1 and minus 1. And this works backwards too. Take any pass from the origin to n plus 1 and minus 1. Find the very first place it hits the line y equals x minus 1. And then, we can reflect everything after that point across y equals x minus 1. What you get is a dangerous pass ending at nn. And this means every unsafe pass to nn are in one-to-one correspondence with all passes from 0, 0 to n plus 1 and minus 1. Thanks to this one-to-one matching relationship, the number of unsafe passes equals the number of passes to n plus 1 and minus 1, which is binomial 2n choose n minus 1. And now we subtract the number of dangerous passes from the total number of passes, and we get our answer. We can simplify this expression to give us 1 over n plus 1 times 2n choose n. This number is also known as the nth Catalan number. It seems that only genius can think of the solution we just demonstrated. Do we have another solution of this problem? And yes, brother, we have it for sure. Let an stand for the number of valid safe paths from 00 to nn. What kind of relations do these values of an satisfy? We can sort all safe passes by where the pass first touches the dangerous boundary line y equals x. Suppose this first touching point is kk. We call these passes class K passes. Now, how many class K passes are there? That brings us to a new question. If a safe pass belongs to class K, we can split it into two parts. The first part goes from 00 to kk. Along this part, we cannot cross the boundary line y equals x. We cannot even touch it. By definition, kk is the very first spot where the pass hits this boundary. So we must not touch it before arriving at kk. So for the first part, we need the number of passes from 00 to kk under these conditions. The second part runs from kk to the endpoint nn. Here the rule is different. We just cannot cross below y equals x, but touching the line is allowed. It turns out the number of passes for the second part is exactly an minus k. The second part is exactly the same upper half region problem, just scaled down to size n minus k. From our definition, the count for the second part is therefore an minus k. Now, how do we find the number of passes for the first part? Since we cannot touch the boundary here, but we can actually shift that boundary 1 unit upward to y equals x plus 1. Now, touching this new line becomes permitted. If we remove the very first and last step of the first part pass, what remains is again another upper half region problem, with a size k minus 1. So the number of passes for the first part is ak minus 1. Since the first and second parts are completely independent, by the multiplication principle, the number of valid passes that first hit the boundary line exactly at kk equals ak minus 1 times an minus k. That is a count for class K passes. For all valid passes from 00 to nn, k can take any integer value from 1 to n. To get our total answer, we just need to sum up all the counts over all classes k. And we can easily see that a0 equals 1 and a1 equals 1 by enumeration. With these two values, we can compute a2, and then a3, a4, and ultimately any an we want. And also, from our first approach for this problem, we also know that an equals 2n choose n minus 2n choose n minus 1, and that also equals 1 over n plus 1 times 2n choose n. So we have now solved the two problems we brought up at the start of the video. You will notice that for both the lattice path problem and the upper half region problem, we have two different ways to work out each one. One approach gives us our result directly using combinatorial choices. The other gives us our final results through a recurrence relation. For the lattice path problem, we can either write down the answer directly with the combinations or set up a recurrence to count everything. The same holds for our upper half region problem. We can get its closed form combinatorial formula via the reflection, or we can split up passes by cases to get a Catalan recurrence relation. These two separate lines of thinking end up giving us exactly the same set of numbers. That is one really interesting feature of combinatorics. The same counting object can be represented both by a direct combinatorial expression and by a recurrence. Last but not least, thank you all for watching the video. I'm Han Ling. See you next time.